using latest CPU features to be a part of the protected domain, but being isolated from the operating system it runs through a hardware barrier. So what is memory introspection? Well, it's basically a technique through which we look at the live operating system image, determine its most important components, code, drivers, user application code, stack, heap, and so on, and trying to determine whether malicious activity is happening inside it. On a lower level, this thing works by, in the case of Xen, we're using the mem-events API and the XenAccess API to hook pages and determine when the operating system has reached a certain stage in its boot process, and then constantly monitor everything it does, when it loads drivers, when it starts processes, and so on. We are able to, this way, to audit pretty much every piece of activity that's relevant to security. That is memory writes or attempts to execute code from places in the virtual memory that should not be executable. And we're also able to veto these attempts, to allow them or to deny them, obviously. This is a big picture of how everything looks after the introspection technology has started to take over some parts of the operating system. So using these hooks that we've set on the memory range of the user domain, we are able to determine the kernel code, its drivers, its, for example, specifically for the Windows operating system, we can determine its driver objects, fast dispatch IO table, the interrupt description table, and so on. We're able to determine when threads are started, when processes are started, and also expanding it to user. So not only the kernel expanding to user, we're also able to determine when a certain process does something that's not really normal for its specific purpose. So for the traditional security product, you will use the kernel features, you will interrogate the registry and so on in order to hook in and protect it as best as possible. In the case of memory introspection, you just look at its hot memory image and try to determine from that to build a reliable image of what is happening inside. That's something not really easy to do, not easy at all. So obviously the biggest challenge is to bridge the semantic between the memory accesses that we've determined and to correlate those with what has happened in the guest, whether it has loaded a driver, whether it has changed the permissions for a page in a legitimate way or not, or a malicious activity. One of the problems we also try to overcome is the overhead related to switching from each user domain to the hypervisor and then to the security virtual appliance, another user domain itself, and to do this as efficient as possible so as to not impact the operating system that we are monitoring. Here's a little history of memory introspection. So it started around 2003, and for Xen it became relevant in 2008 with a research with a project named Ether. That's actually what we've used to start our own research on Xen. Up until then, we had custom build technology for this. So a couple of Xen features which were necessary in order to do this. The most important one were the mem-event patches that appeared around 2009, which we used to be notified each time a certain type of memory EPT violation actually happens. In 2010, when the project was in full motion, we started to looking at libVMI. So up until then, the technology was running with the same privileges as the hypervisor itself. So we started thinking, well, let's move it to user space. So we looked at the libVMI in order to do this. Unfortunately, at that time, there were a couple of limitations which prevented us, like it was impossible then to map into a user domain pages from a different user domain. The ability to read the CPU state was involved more trips to the hypervisor and then to the introspected domain. So we started our own version of libVMI from the ground. It only took us about 2 weeks because it is much simpler than libVMI. We have a lot less requirements. In 2014, we published a set of patches to Xen Devel. They bring a number of changes, such as with each memory event, we pack the register state for each vCPU. We've also enabled we've also added the possibility to be notified each time a certain MSR is changed. We've also added the possibility to emulate an instruction without allowing it to actually write to memory. This is very important. And also the ability to inject page faults into a user domain. Some of them have already been accepted. On some of them, the discussion continues. So here's a really simple picture of what we have added to the memory events. So that's basically a structure that is packed from Xen and sent to user space and received via libxc. And this is a larger picture of what we hook in and are able to build an image of inside our introspection, inside an introspection technology. Not necessarily ours. We are hoping more security vendors will jump and bring their own technology. So based on the changes we've made to Xen and published, we've been able to enhance our own introspection technology and are able to add security against rootkits. That was the primary purpose of the project. And then expanded it to user space. So we're now able to determine each time a process is started. We're able to determine each time a process attempts to inject code into a separate process and determine whether that injection is a legitimate or a malicious one. We're able to determine each time a process attempts to execute code from either stack or heap. We're able to determine when code is unpacked, and we can also react to all these events by injecting a, let's say, remediation tool on the fly without using any kind of help from within the guest. That remediation tool is injected as a process in the user domain on the fly and removed upon completion of its task. The introspection logic itself, that is reacting to events and taking a decision whether to allow or not a certain activity, has very small overhead. It is smaller than the overhead added by the transition from one domain to hypervisor and then the other, which takes the decision itself. I'm going to add something here. So I said earlier, we added the ability to emulate instructions and not allow them to write to memory. That's very important for the introspection technology, because each time we determine a malicious activity, we're able to, well, a page fault, an EPT exception is raised, and we're able to emulate that instruction so as to advance the instruction pointer and have a consistent register state, but without changing the memory that it wanted to alter. So the malware itself usually lives with the impression that it has done the damage, when in reality it hasn't. Another important thing is the ability to inject faults into the guest and bring pages which are either swapped or mapped and not yet brought into the active memory. That's been a bit of an ongoing discussion on the Xen devel, whether it is possible to do that in a reliable way so as not to mess up the operating system. It is. And if you like, we also can do live demos of this. And here, Ravi is going to talk about upcoming processor features, hardware features, that are going to make memory introspection even more efficient, if possible.
Thanks, Mihai. My name is Ravi, and I'll cover some of the topics, or dive deeper into some of the topics that Jun covered a little bit today morning in a different context for the NFV performance optimization. This use case is, as Mihai was describing, more in the context of memory introspection. So when you look at memory introspection, as Mihai covered, the functionality at the brass tacks levels is really in sort of two spaces: CPU state monitoring or memory state monitoring for change control. Right? You're trying to basically do integrity of specific data structures to make sure that you can look at them as they're changing to basically access control those changes. Right? And there may be valid changes happening to those structures in memory. The main point is having visibility into when those happen. And the factors that limit VM memory monitoring performance are some of the ones that I'll cover. The other point that Mihai also brought up was lack of memory isolation. Today, the only way for us to achieve memory isolation is to separate components into different VMs. And some of the things that Jun covered earlier on, like protection domains using EPT structures, can also be used to protect components within an operating system. And that sort of feeds into the use case Mihai was describing. And then I'll talk about specific intrinsics to actually address performance gaps depending on whether you're monitoring execution events or access controlling data rights, because both are needed from a VM introspection perspective. When you're trying to do runtime integrity, you can't just say, oh, I've made the code immutable and I'm safe from attacks, because a lot of the stealth attacks will actually go in and target data regions and will completely subvert the OS by just modifying driver dispatch tables, for example. And I'll describe some of the Xen extensions or patches that we are currently working on, and hope to send those out into the community for RFC once we've addressed some of the opens in those. So the factors that limit VM memory monitoring, one is obviously the round trip time, right? The latency to context switch into the hypervisor and back into either the same guest or a different guest. And this is both for, it sort of comes down to what is the frequency with which you take those events, whether you're monitoring execution or data accesses. And obviously, if you're monitoring dynamically written data structures that are normally written to by the OS, you will see that many more events as you're access controlling those, right? The second aspect is how much better can you filter those events? Since today, the architecture, x86 at least limits us to 4K granularity of memory monitoring. We have to monitor memory at the finest granularity of 4K. And so you end up with, when you're trying to do VM memory introspection for existing operating systems, where you don't have the liberty to go in and modify the layout of data structures, you end up with a lot of fault sharing cases, where you take events, but for the most part, you may be just allowing those events to go through. And then as we look at cases like VMM nesting, those applications of memory introspection just explode in terms of performance overhead, because you end up taking nested EPT violations that you have to manage between the root hypervisor and the guest hypervisor. So our design goals were sort of how can we address these three vectors and support these use cases. So Jun covered this today morning in the context of NFV. I'm basically showing here the same model, but in the context of isolating components or code within an operating system, right? So Xen creates multiple EPT structures today, but really manages it in the context of the P2M for each domain that it creates, right? And the notion of using multiple EPTs is architecturally defining multiple EPT hierarchies that at a very basic level are exactly the same in terms of the memory mapping that they do, but differ in terms of permissions. What that gives you is a very simple construct by which you can associate specific code with specific data with the right set of permissions. And I've just shown here a simple example where on the top you see some OS kernel data and code that has access, read executable or read write based on the whether it's code or data, and all of the driver code and the driver data is essentially inaccessible from a perspective of either executing the driver code or accessing the driver data. The point being, when the driver code is actually called back from the kernel, the hypervisor has a chance to access control those points. This is sort of how the legacy architecture behaves, right? Where you take an EPT violation, and the EPT violation will let the hypervisor check potentially an entry point on the driver code page and allow the execution to continue by manually modifying the EPTP, right? This is how it would work in a legacy architecture. So when we wanted to address this lack of isolation, and this is a similar picture to what Mihai showed, where you have security filters in the kernel or security filters in user space, which are basically relying on seeing certain events that are occurring and access controlling them. You have to really do that without sacrificing performance, since even if you can isolate components using EPTs as they are defined today, you really have to be able to handle legal execution points where execution is crossing these domain points, whether it's callbacks into the driver object or data accesses that the driver is making on its own memory state that it allocates for itself, right? Because it's also important to protect that dynamic data structures or dynamic data for the security engines, because if that's exposed, a stealth malware can just go in and disable the security engine, for example. So that was sort of one of our key design goals, is how do we eliminate these induced VMExits, since by construction the hypervisor is inducing these VMExits where they would normally not occur. So VM functions was added as a general intrinsic for with the notion of supporting services from the CPU for specific VM guests. And as Jun was describing in the morning, one of the leaves designed for VM function is dedicated for EPTP switching. And the whole point behind VM function is it's sort of the opposite of a VM call, where a VM call is an explicit intrinsic to request services from the hypervisor. VM function is designed to, in the normal case, not exit to the hypervisor, but use services from the CPU that are set up by the hypervisor, right? So the security model is still under the control of the root hypervisor, and the CPU provides that service without a VM exit as long as that contract is observed, right? If there's some invalid execution of the VM function, the model is to exit out into the hypervisor. So let's see what the VM function based domain switching looks like. And you guys already saw the high level idea, so I'll actually dive into a little bit more details. But the concept is the same. The hypervisor sets up multiple extended page table domains, and I'm showing just one sort of DOM U here, the VM0. And the point is basically to have components in the guest that are sort of paravirtualized or enlightened that invoke VM function at the point at which they want the traversals to happen from untrusted code into trusted code or vice versa, right? And the policy is sort of encoded at install time or at protection domain creation time by the hypervisor, right? Where otherwise with legacy architecture, it would be taking an exit and applying that policy that, hey, is this entry happening on this code in this code page, then allow that access to go through. And the way the feature is configured is by the hypervisor creating the EPTs like it does today, but actually recording those EPTPs, the root pointer for the EPT tables, into an architecturally defined page that's pointed to from the VMCS, so that when the guest invokes the VM function, the hardware knows how to find the right EPT context to use. And as I said earlier, the security policy is under the control of the hypervisor. So if the hypervisor wants to invalidate a view or disallow VM functions into a certain view, it simply has to either invalidate the EPTP at that index or not locate it in that index at all, right? So the other problem is there are still asynchronous induced VMExits, right? So you can control synchronous VMExits by placing them into your code path wherever you want the execution to cross across protection domains. There are also cases where you're monitoring data in place and you don't know when that data write is going to happen, right? So whenever that data structure write happens, in legacy architecture, even with separate protection domains, we would have to basically exit into the hypervisor, either emulate that access in the hypervisor, or switch back into the guest with a control like monitor trap flag to essentially single step those accesses. And this is fine to do as long as the data structures are very static and they're not being modified in the normal course of operation. But if those data structures are dynamically modified by the operating system, this can lead to a lot of overhead as you're monitoring those data structures, or due to false shared data on the same 4K page, which are frequently accessed by the operating system or some other component in the guest. And obviously a side effect is it also increases complexity in the VMM, because you now have policy that you're sort of embedding in the VMM for different types of guests. So the other construct that we wanted to introduce was the notion of virtualization exception. The whole idea with virtualization exception was, since the policies are really coming from this enlightened guest service, security service, that has notion of how it modified the EPT permission to cause the EPT violations in the first case, why not give the VMM a safe way to report those violations back to the security agent where the VMM wants to allow it, right? So the notion with virtualization exceptions is to mutate EPT violations into a new exception that's reported through the guest IDT, and it effectively also reports additional information to the guest through a structure called the VE info page. This is a specific page that's negotiated between the security service in the guest and the hypervisor, where the hardware will deposit state, which looks very similar to the kind of state the hypervisor sees today in the exit qualification, right, when we report a EPT violation. The key point behind virtualization exception is, as this flow shows here, using some of the other intrinsics like VM function, you can now allow that access or access control those write events without actually causing any exits into the hypervisor, right? So you set up the policy on the EPT page. If the hypervisor is okay with that EPT violation on those pages being converted into a hash VE, it can turn the hardware on to do that. When the write happens, that's reported as a hash VE into the security agent, which can safely use a VM function to switch into a view where it can access control that write. Now, it can choose, the guest software can choose to emulate it in place, or if the instruction is like a RIP relative or some other case where it's harder to emulate, it can also single step it through a special purpose view created to complete that write access. So it also gives the guest software more options to handle those events, and it removes all the complexity from the hypervisor. The hypervisor is basically supporting some bare mechanics. It doesn't need to be concerned about how the policy is actually being implemented by the guest software. So this is just a sort of one slide view of what you would find in the SDM for VM function configuration. As I said earlier, it's an opt-in capability, so the hypervisor has to explicitly turn VM function on. Since VM function is a leaf-based instruction, the hypervisor can actually choose to turn on specific VM functions and turn off others that it does not want to expose to the guest. And for EPTP switching specifically, if that's active, there is a new page that's referenced from the VMCS that contains the alternate EPTP structures that are managed by the hypervisor. So it can set up the views that the memory views that it has created, right? And obviously, if 512 is sort of a architectural limitation for VM function, the hypervisor can obviously manage more than 512 and sort of switch between complete table structures. So it can manage it like a cache. The other key point is, if there are any errors reported, errors that occur during VM function, for example, an invalid index is used that doesn't refer to any of the indexes that are possible architecturally, or if the index refers to an entry in the page that's actually an invalid EPTP because it has a reserve bit set, those are all consistency checked by the CPU and will generate a VM exit with a new VM function exit reason. So the hypervisor can go check exactly what caused that erroneous VM function, because it may be a malware attempting to just VM function into an invalid view. The other key point here to note is that since hypervisor is, we wanted to keep the policy sort of really under the ownership of the security software. VM function doesn't perform any additional checks of where that code is executing from. It's really up to the hypervisor to set up the memory permissions on the pages on which VM function executes for it to hold the security properties. That's why the view construction or the way permissions are set up on the view are very critical for VM function to work correctly. Similar view on virtualization exception. This is also explicitly a new capability, so it is opt-in for the VMM. And the key point with virtualization exception is there is a new bit in the extended page table entry that gives the hypervisor the control to selectively suppress virtualization exceptions. So if the hypervisor has pages that it is, for example, sharing across VMs for copy on write cases or other scenarios where it has protected memory for certain emulated device regions, it can explicitly set suppress VE on those, and those would just give you legacy EPT violation behavior. For memory that it has explicitly assigned to the guest and it wants to allow the guest to change permissions for memory introspection purposes, it can disable suppress VE and let the guest handle those events. So the Xen extensions or the patches that we are currently working on sort of fall into these 4 categories. And we wanted to coordinate with Mihai and his team, since they were talking about some similar capabilities in terms of modifying, letting the guest software sort of modify EPT permissions and things like that. So the first sort of patch is a generic patch that applies to a lot of the use cases more generally, which is why we separated it, which is the efficiently sort of creating and maintaining the alternate EPT views. That's kind of a orthogonal functionality in and of itself, so that makes sense as a separate patch. The second one was hypercalls to edit EPT permissions without conflicting with Xen's current EPT management. So this effectively boils down to adding a new memory type so that Xen can basically allow the guest to modify, read, write, or execute permissions. The third one is sort of the x86 specific patch, which is if virtualization exception is seen as a capability in the VMX capability MSRs, allowing the VMM to turn that on and report the events through #VE. And then finally the VMFUNC configuration patch, which allows if the alternate view support is there in the hypervisor, then if it sees VMFUNC capabilities, it can use that for accelerating those events, right? And this figure is just meant to sort of give a high-level view that now you can have security engines which have completely different policies across different guests that own their own handling of events without Xen having to do any custom logic for either of these. The other key point I wanted to note that actually I should just use this slide. So coming back to these three areas, right, that we started off with in terms of introspection performance improvements, the round trip time, even though the hardware has been improving round trip time at sort of a regular pace over time, since these workloads really, depending on the kinds of policies you use, these really push the envelope in terms of the amount of events you take on the system. We really want to address them with very efficient techniques like VMFUNC and #VE. So that sort of addresses your round trip time, because there isn't a round trip time if you use these techniques as they're intended to. The other part is filtering the events. The current architecture doesn't really address filtering events, because you can still have false sharing #VE events on the 4K pages, because the memory granularity is still 4K, but #VE being a lower latency event than taking a full context switch gives you some scalability back in terms of handling those events with lower latency. With our experiments, we've seen around a 5x difference between handling events via #VE versus taking a VMExit. And with VMFUNC, we've seen around an 8x difference in terms of doing view switches through VMFUNC versus through the hypervisor. The third point, which sort of falls through directly from the first two, which is the round trip amplification. Obviously, with these models, if the root hypervisor is opting into these capabilities and it exposes it to a guest hypervisor that uses it, none of these events cause any VMExits, and therefore they don't cause any nested VMExit or any amplification of events, right? So the idea is, if the inner guest is using memory introspection using these techniques, when it sees an EPT violation on a page that's protected this way, the #VE event is directly reported to the inner guest when that happens, right? So just to conclude, Mihai, I can cover some of your points as well. So I think Xen has a good base today for providing a good generic memory introspection engine interface. As Mihai was describing, using a separate domain, we can achieve agentless security to address some of these stealth attacks, and sort of using some of the other techniques that I described, even if you have an agent that's running within the guest, you have some techniques available today to isolate those to a much better degree than was possible before, without losing performance for doing scalable memory introspection. So, and our patches should be coming out in the next week or two as we resolve some of the open issues we know of. That's it.
One question which we're already 5 minutes on the schedule.
Sorry.
Go ahead.
I was wondering how the exceptions would be triggered. Exactly what programs and how are they programmed?
So the way they're programmed is you set the permissions on the EPTs like you do today, right? So in this case, the security agent would request the hypervisor to change, read, write, execute permissions on some pages. And if on that VMCS you have activated the virtualization exceptions and not suppressed virtualization exception on that EPT entry, then when a EPT violation happens corresponding to that mapping, the hardware will automatically generate a virtualization exception on that CPU.
Yeah, just hi, Bob. For those of you who have questions, we'll be hanging out on the side, but more importantly, we're hosting a cocktail party tonight, so I know once everybody has a drink or two, the questions become a little bit more less formal. So come on by tonight.
Awesome.